before going deep into the potential energy, one thing to be noted for is, see, potential energy exists only for conservative forces. Right? And since electrostatic force is a conservative force, we have something called as electrostatic potential energy. Okay. Now, what is this equal to? See, the electrostatic potential energy means, suppose there is a charge Q1 present here and there is a charge Q2 present here, right? So, how did they come? Basically, it might have been that first you bring charge Q1 here, then you bring charge Q2. So the potential energy of the system is the work done to establish the orientation of system. Now interaction, here we have interaction energy. Now what is interaction energy? Interaction energy is the work done by an external force to bring the charge from infinity very slowly, which implies acceleration is 0. Okay, and see, the basic, you might be knowing that the potential energy basically is not defined at a point, it is related to some point. So whatever we do here is we take reference to infinity, and then we say that u at infinity is equal to 0. Now taking that reference, we do all our calculations. Okay, so let us now calculate the interaction energy for this particular system. Suppose this is the system. Suppose Q1 is already present and we need to bring Q2 from infinity. So what is the force acting here due to Q1? This is in this direction, K Q1 Q2 by R square. Suppose this distance is R. Now for the acceleration to be 0, one needs to apply an external force of K Q1 Q2 by R square in this direction. Now what is the work done by the external force? F dot dr, which is equal to now see, dr is in this direction and f is in this direction. So since they are anti-parallel, we include a -1 here, because cos 180 degrees will be minus. So this is small work done. Now we integrate it and get the expression. From 0 to infinity to R. So on integrating we get so for this system the interaction energy is equal to this much. Okay, so this is, we don't have to solve now, from now on, for the interaction energy between two charges, we don't have to solve every time taking infinity to R. Now if we remember this as a formula, like the interaction energy between two charges placed at a distance r is equal to k times q1 into q2 by r. Now based on this formula, let us solve this question. So in this configuration, we have a charge q here, q here, q here and q here, and we are required to find out the potential energy of the system. This is the side A. So see, potential energy is firstly this and this, this and this, this and this and this, combination of two charges. Okay, so since there are 4 charges, we have to get 4 C2 combinations, which is equal to 6. Now see, this is 1, 2, 3 and 4 combinations. 4 times, what is the potential energy between these two? K q times q by a square. Okay, plus now there is one more pair of this and this. This is 2 times k times q by, the distance is root 2, right? So it becomes 2a square. So this gets this cancelled. So ultimately the answer becomes 5kq square by a square. So this is how we calculate the potential energy. Now we go on to our next concept of electric potential. How did we find out the electric field? We said that force by a test charge is equal to electric field. In a similar manner, we define potential, electric potential, as the work done to bring a unit positive test charge. The amount of work done to bring a test charge at a point from infinity is termed as electric potential. Okay, so it is basically equal to the interaction by Q, the test charge. So now let us find out the electric potential due to a point charge. So electric potential due to a point charge is equal to, see let this point charge be Q. I am bringing a test charge Q1 from here, so till I brought it to a distance r. We know that the work done to bring this charge is kq1 by r. So electric potential V is equals to W by Q1, which is equal to kq by r. Okay, so this is the potential due to a point. Now next we go on to, see, I'm not deriving it very getting involved, because we have done the same thing while discussing about the concept of electric field. So I'm running a bit fast here. The main difference between the electric field and electric potential is electric field is a vector. But potential is not. Okay. So now let us try to find out the potential at the center of the ring. Are we? Now see, consider a small element dq. Now what is the electric potential dV at the center? dV due to that dq is equal to k times dq by capital R. Now the net potential V here will, see, initially in electric field thing, for every point we had to convert this into 2 different directions, because there was a thing called direction which was hindering our process. But since the potential is a scalar, we do not bother about the direction and simply integrate it. So see, Ky r is a constant, and if I integrate dq whole ring, I get q. So if q is the total charge present on the ring, the potential at the center due to the ring is equal to kq by r. Now let us find out the potential at the center of a disk. This is a disk, okay? So for disk, what I do, I go to a distance r, consider a ring. So the small potential at the center due to the ring will be equal to dq by r. Now I simply cannot integrate here because r and dq are related. Now suppose the surface charge density is sigma, then dq will be equal to sigma times 2 pi r times dr, right? Thus the dv is equals to k sigma 2 pi r dr by r. So r gets cancelled. We get 2 pi k sigma times integral dr. R from 0 to r is capital R. Okay. Now what is the total charge? Total charge is equals to sigma by pi r square. Sorry, sigma is equals to q by pi r square. So q is equals to, q by r is equals to pi sigma r. So pi sigma and r. So this will be equal to k q by r. So this is the potential at the center of the disk. Now let us find out the potential due to a rod at a point D. Okay, so again I consider from here at a distance x a strip of length dx. Now the potential due to this here is equal to k times dq by x plus d. Okay, and dq here is equal to lambda dx. So this is equal to k lambda dx by x plus d. Now integrating it, I would get limits as 0 to this length is L. So this is equal to k lambda ln L plus d by d, which is equal to k lambda times ln. So this is the electric potential at a point which is at a distance L from this thing. Okay. Now we find out the electric potential at a distance x from the ring, charged ring of, okay, this distance is x, this is r. Consider dq. So electric potential here due to that small element is k dq by under root of x square plus r square. See here, x is constant, r is constant, k is constant. So simply integrating it, we would get kq by, okay. See, finding, like if you are very well versed with the ways of finding out electric field, then like applying them to electric potential is not a big deal, and it's almost a very easy task. Now let us apply the same thing for a disk. Okay, so go at a distance r, consider a ring. This is x, this is r. We need to find the electric potential here. So dV due to this ring is equals to k times dq, the charge present on that ring, times x square plus small r square. Now here r is not constant, so we need to, and it is related by q. Now dq is equals to sigma times 2 pi r dr. So dV turns out to be K sigma 2 pi R dr by under root of x square plus r square. So V is equals to integral 0 to capital R 2 pi sigma K R dr by under root of x square plus r square. Okay. Now I put x square plus r square is equal to t square. So which means r dr is equals to t dt, and this would turn out to be, see, when r is 0, t is x, and when r is capital R, t is under root of x square plus r square, and this turns out to be 2 pi sigma k t dt by t. So this and this gets cancelled. So this is equal to 2 pi sigma k times t, which is x to root over x square plus r square. This is equal to 2 pi sigma k root over x square plus r square minus x. So hope all these methods are clear. In the next session we will learn a bit more about finding out potential energies of systems, and then applying them to a few more questions based on conductors and all. That's why we will read a few more properties about the electric field and its relation with the potential. So first point being, direction of electric field is such a way that the potential decreases maximum in that direction. Yeah. So this is one important point. See, suppose the potential, say here is 10 volts and here is 5 volts, and say potential here is 5 volts and here is 4 volts, here is also 4 volts. So see, in this direction, sorry, here is 6 volts and here is also 6 volts. So the decrease in this direction is 4 units, and here is 4 units, here is 5 units. So like if only these three are the different potentials, then the direction of electric field will be in this direction, because here the potential difference is, like, the decrease in potential is the maximum. Now why is it so? See, we know that the potential energy U is equals to force external dot dr, right? And now force external is equals to minus of force of electrostatics dot dr. Now this is equal to minus q e vector dot dr. So what is U by Q? It is basically D. So where is it, like the dot product, considering like dr the direction, in the direction of, like, the direction of electric field is such that, see, when the drop will be maximum, the drop will be maximum when both E and dr are in the same direction. So whenever the potential decreases maximum in that particular direction, so like when we fix a direction, it means that we are fixing dr. So in that direction the electric field also should lie. Only and only then the potential decrease will be maximum. Okay. Now from here, see, suppose if we take the the direction to be specified such that the decrease in potential is maximum, then from here we say that minus E is equals to dV by dr. So E is equals to minus dV by dr. So now what do we conclude about the electric field? Electric field's magnitude is equals to minus dV by dr, and direction is in such a way that the drop of potential is maximum. Okay, so now based on this particular point, let us solve a question. See, we are given that the potential in a region varies as okay. Now we are asked to find out the electric field at 1, 2, 3. So now from what do we know? What do we know from here? Like, what is Ex? Ex equal to minus dou V by dou X, where dou is the partial differential, which is equal to, see, if I differentiate this with respect to X, like everything else being constant, this will turn out to be 2y, this is 0 plus 7z. At 1, 2, 3, this will be equal to 2 2s are 4 plus 7 3s are 21. Okay, now Ey is equal to minus dou V by dou y. This is equal to minus 2x plus 3y. This is 3z. This is equal to minus 2x are 2 plus 3y 3z are 9. What is Ez? So this is equal to minus of 10z plus 3y plus 7x. This is equal to minus of 10z is 30 plus 3y is 6 plus 7x is 7. So the electric field is equal to minus of 25 I cap plus 11 j cap plus 43 k cap. Okay. Yeah. So see, now let us solve. Now let us go to the concentric shells. See, I say that initially this shell is given a charge 2q, this is given a charge 4q, and this is given a charge 6q, and this and this are connected, and is earth. Now here I am trying to introduce the concept of earthing with this question. Now what does earthing mean? Earthing means that, see, to whichever conductor we earth, the potential of this conductor becomes 0. Okay. Now this is R, this is 2R, and this is 3R. So now what is the charges distribution? Okay. And also earthing means connecting to earth. It means that now there is an external link between the earth and the what do you say? Sorry, let us not introduce this thing first. There is no link between these two these things. And yeah, this is earth. So Now we need to find out the charges distribution. So basically, see, since here is no charge, we get here 0, we should get here 2q, we should get here minus 2q, 6q, minus 6q, and here it should be 12q. But ideally it should be so, but here it won't be in this fashion. Why is it so? See, whenever we earth a particular conductor, its potential becomes 0. So now we have to distribute the charges in such a way that the potential of this conductor becomes 0. And also, see, when we are earthing, now we have the liberty to change this charge. Now this charge will not remain constant because it has got another source from where it can gain or it can give the charge. So basically, see, whatever we did till here is correct. This is minus 6q, that is also correct. But now let the net charge on this be q. So what is the potential over here? Due to this charge, it is k times 2q by 3r, plus due to this charge it is k times 4q by 3r, plus k times q dash, let this be q dash by 3r. Now this should be equal to 0, which means that q dash plus 6q should be equal to 0, which means q dash is equal to minus 6q. Thus the net charge on the final, this thing should be minus 6q. Thus it turns out that this charge is, the charge on the outer surface is 0. So basically whenever we earth a conductor, we say that its charge is 0. Now let us solve even bit more complicated question. See, this is 2q, this is 4q, this is 6q, and now there is no earthing, but I say that A and C are connected with a wire. Okay, and again this is R. So here what is happening? See, since they both are connected, now there will not exist any potential difference between the two. So whenever there are two conductors connected with a normal wire, its potentials are equal. Also, now the charge from A can transfer to charge C and vice versa. So let me consider that finally the charges are q dash on A, it will be 4q on B because there is no other connection, and see, the net charge acting on, like net charge on A plus C should be 2q plus 6q. So here it is 8q minus q dash. Okay. Now what is q dash? So basically, what is potential of A? See, potential of A is equal to, due to this charge, it is k times q dash by r, plus due to this sphere, it is k times 4q by 2r, plus due to the outer thing, it is k times 8q minus q dash by 6r. So this is equal to by 6r times k 3q dash plus 12q, sorry, here is 6q dash, 6q dash plus 12q plus 8q minus q dash, which is k times 5q dash plus 12q by 6r. So this is the potential at A. Now what is potential at B? Sorry, potential at C. Potential at C due to this thing is k times q dash by 3r, plus due to the middle one is k times 4q by 3r, plus due to the outer one is k times 8q minus q dash by 3r. So this turns out to be 12kq by 3r. Now this potential and this potential should be equal. So which means that which basically means that k times 5q dash plus 12q by 6r should be equal to 12kq by 3r. So 5q dash plus 12q is equals to 24q. So q dash is equals to 12q by 5. Now, which means that here we have the finally we have the charge of 12q by 5. Here we have 4q, and here we have 40 minus 12 is 28q by 5. Right? Now how will be the charge distribution? Since inner we have 0 charge, it is 0 here, 12q by 5 here, minus 12q by 5 here. So here it will be 32q by 5. Here minus 32q by 5, and here 12q. Right? So this is how the charge distribution will finally occur in this thing. Now what if I add another twist and I say that, see, this is earth. So if now B is earth, see, this wouldn't affect this charge, okay? The charge on this will still be 12q by 5. Sorry, it will affect. So now what does the equation become? See, now let me erase this up and draw it up again. Okay, so now let me assume that this has QA, this has QB, and this has 8Q minus QA. Right? Now what is VA? See, VA is equals to K times QA by R plus K times QB by 2R plus K times 8Q minus QA by 3R. What is VB? VB is equals to K times QA by 2R plus K times QB by 2R plus K times 8Q minus QA by 3R. Now what is VC? VC is equals to K by 3R times QA plus QB plus 8Q minus QA. Right? So now what are the equations we know? We know that VA is equal to VC and VB is equal to 0. So firstly, substituting VB is equals to 0, what do we get? We get QA plus QB by 2R is equals to QA minus 8Q by 3R. So 3QA plus 3QB is equals to 2QA minus 16Q. So QA is equals to minus 3QB minus 16Q. This is one equation we get. Now, see, substituting this thing in VA equal to VC. Now for VA equal to VC, what should we get? We should get, see, 6QA plus 3QB plus 8Q minus QA by 6R should be equal to QB plus 8Q by 3R. So which means 5QA plus 3QB plus 8Q is equals to 2QB plus 16Q, which means that 5QA is equals to minus QB minus plus 8Q. Now what is 5QA? 5QA is equal to minus 15QB minus 80Q. So from here we get 14QB is equal to minus 88Q. Thus this 7s are 44s are QB is equals to minus 44 by 7Q. Now substituting it here, so QA is equals to minus 3QB minus 16Q minus 44 3s are 132 by 7 minus 16q. This is equals to 7 6 are 42, carry 4 11. So QA is equals to right. So finally we have a charge of minus 244 by 7q here. We have a charge of minus 44 by 7q here, and then we have a charge of 8q minus qa. So 8 and 42 minus 244. So minus 202 by 7q here. So this is the configuration if we arrange it in this manner. Thus, I think that the concept of earthing is clear to you all. Earthing basically means that to whichever conductor the earth is connected, we make the potential of it to be zero. And an important point to notice, at that moment the charge will not be conserved, because like the charge, 1 minute, sorry, here it is 8q plus, so it becomes 56 plus 244, so this is 300. So ultimately it becomes like the charge will not be constant, like the charge can move and move out and in of the earth, and thus there can be an increment or a decrement in the charge. So this is all about the concept of earthing. Now finally, last concept which I would like to tell to you all people in this topic of electrostatics is of self-energy. See, if you try to write the potential energy of the system, it is basically the energy required to get all the particles in the configuration which they are present in right now. So what did we say earlier? We said that if there are two charges, Q1 and the other one being Q2, we said that the work done to bring this charge from infinity in the presence of this charge is equal to the potential energy of the system. But actually it is not. It is only called the interaction energy. There is something called as U self energy. When does this come into action? It comes into action whenever we have extended bodies, like a sphere, like a solid conducting sphere. Suppose I have a system of a sphere charge capital Q and a small charge Q. Now we may say that the energy of this system is, suppose the distance is r, k q by r, but this is not. This is only the interaction energy. So the total energy is found out by something else. So basically the total potential energy of a system, U total, is equals to U self plus U interaction. Now how do we find out the self energy? See, I'll give you an example of finding the self energy for a solid sphere, which can be applied to any other thing. So let there be a solid sphere of charge Q. So see, at any instant, like at some instant, we say that the charge is small q and r, and there is the intake of a further more charge of dq. So what will be the work done here? So dw is equals to the potential right now times dq, right? And what is the potential? Potential is kq by r times dq. Am I right or not? Thus, now what is kq by r? Now r is C. Q and r are related. We know that the volume charge density should remain constant. So the volume charge density means that Q by 4 pi r cube, 4 by 3 pi r cube should be equal to rho. So Q can be Q can be written as 4 pi rho by 3 r cube. Thus dq will be equal to 4 pi r square times rho times dr. Okay. So this here will be equal to k times four pi rho by 3 r cube by r times 4 pi r square times rho dot dr. So this is finally equal to k times 16 pi square rho square, this r and r gets cancelled, r power 4 dr by 3. Now integrating it from 0 to r, we get 16k pi square rho square by 15 r power 5. Now what is rho? Rho is equals to q by 4 pi 3 pi r cube. So here on substituting that, we get the work done as 16k pi square, rho square is 9q square by 16 pi square r power 6 times 15 times r power 5. So 16 pi square gets cancelled, r power 5, r power 6. So 9k q square by 15. So 3k q square by 5. So this is the self energy of a solid conducting sphere. For every similar object, we find the self energy in similar manner. Now, having found out this self energy, now what we say, see, if we have a system of this kind, that is a solid sphere of radius r and a small charge q placed at a distance small r, then we say that the potential energy of the system is its self energy, which is 3k q square by 5 plus the interaction energy. Now how do we find out the interaction energy? The potential at this point due to this whole charge body is k capital Q by small r times the charge present here. So this is the net potential energy. Hope this is clear. This we can use in finding out in solving out questions which involve work energy theorem as its base and etc. So this is all from electrostatics. Hope everything was clear and all the best.